Alright, so today we're going to talk about tangent planes to a surface, or the tangent plane to a surface at a given point. Let me pull my markers and see what we're doing here. So let's say we have a point. By the way, let's write this function. Let's say that this function is something like z equals f of xy. And let's say that that color is not very visible. Let me write with green that z is f of xy. Alright, and now let's say that we pick a point here on the curve or on the surface. Let's say we're there. Let's say the coordinates of this point are going to be given by, not vector, but point x naught, y naught, z naught. And z naught, of course, because that is on the curve, that point is on the curve, z naught will be nothing but f of x naught, y naught. Because why not? Terrible joke. Alright, so now what we're interested in finding out is a plane that is tangent to this surface. So something that would go kind of in this direction. That's going to be tangent to this surface at that given point. So what do we know about planes? Well, the equation of a plane that goes through the point x naught, y naught, z naught with and it is perpendicular, so it goes through this perpendicular to or orthogonal to perpendicular to the vector ax or abc is going to have an equation, if you remember, a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. So that is the equation of that plane. So what do I need? Well, I need to find that vector that would be normal to this plane here. And that vector, we can call it n, if you will. Alright, so now we have to ask ourselves a question. How do I find a vector that is normal to this plane? Well, it would suffice for me to find two vectors that are on the plane, do the cross product between them, and obtain the equation of that vector, or the form rather of that vector n. Once I have n, I plug it in here. So by the way, I'm going to call this one n, just the normal vector, just so we have it in view. So let me erase this, and then I'm going to show you how to find those two vectors. But I first wanted you to have an idea about what is it that we're trying to do and how we're going to do it. So let me erase, and I'm going to be right back. Alright, so let's return to what we were trying to do. So I need to find those two vectors I talked about. So let's figure out how we can do it. So the easiest way to do it is by taking this plane, x naught, and cutting the surface in that direction. And so when you cut it, then you're going to have some curve that will intersect where the plane intersects the surface. So you'll have that curve right there. So let's draw that over here in the plane x equals x naught. So in that direction, you just have your coordinates y and z, and you'll have a curve that looks sort of like this. Doesn't have to be exact, we're just trying to get an idea. And now x naught, that coordinate is fixed now, but I do have y naught somewhere here and z naught here. So if I calculate the equation of the tangent line to that curve at that point, then I can find a vector on that tangent plane that I'm trying to find, because if I find the if I draw my plane again, well, the vector that is tangent to this curve is on this plane, because the whole plane is tangent to the curve. So I need to find this one, and what I'm going to do is, well, what do I know? Well, how do you find the, I'm looking for the marker I have in my hand. You're looking for the derivative of this function at this point, but you're thinking about this function as a function f of x naught comma y. Y is the variable, x naught is fixed. So z f of x naught comma y. Now x naught is fixed, y is a variable. You can take a derivative with respect to y. When you take that derivative, what will you do? You do the limit as h goes to 0 of f of x naught comma y plus h minus f of x naught comma y over h. That is the partial derivative. So the slope is going to be given by the partial derivative of f with respect to y evaluated at x naught comma y naught. Ooh, I got very close to the edge. I think I got it in. So that partial is going to give me the slope. So how do I find a vector based off of that? Well, you go from y naught to y naught plus 1, and you write a vector that goes from this point to this point. Okay? And so from this point to this point, you're going from x naught comma y naught, oops, not x naught, y naught comma z naught. Sorry about that. We're in 2 dimensions. X naught is fixed anyways. So we're going to from y naught comma z naught. I wrote x naught. Oh, correct, because x naught is fixed. Everything is good. Don't stress. So y naught comma z naught, and I'm going towards y naught plus 1. And then what do I get? Well, z naught is going to be the same z naught, but you're going to be adding the slope. Why? Because I went 1 unit to the right, I go the slope up. In this case, the slope will be negative according to my graph, so I go down. So that would be that, and so my vector here would be 1 comma m. And m is the partial derivative with respect to y of x naught comma y naught. So this vector that I drew here, that vector right there would correspond now in 3 dimensions. What was my change in x? Nothing. X was fixed. So I get 0 for the change in x, 1 for the change in y, and m, which I'm going to write just as fy. Evaluated at x naught comma y naught, but for space sake, I'm going to write it like that. Okay? So that's one of the vectors. Now, if I, instead of cutting on this plane x naught, I would cut on this plane y naught. And this is going to start getting a little bit messy, but I'm going to transport it to the other side. So I would get, let's try to draw it in pink. I would get a curve that looks kind of like this, in this direction. So if I do the same thing, that would give me another vector that would go in this direction. And that vector, you can compute it, would be given by 1 comma 0 and then the derivative with respect to x. I'm not going to derive that one because the graph is already looking really busy. But those are the 2 vectors that I'm going to use. And now with the cross product, I'm going to get my vector n. And then I'm going to get the equation for the plane that is tangent to the curve at the point x0, comma y0, comma z0, where z0 is f of x0, comma y0. I said a lot. It's better just to write it. All right, so let me erase here, and I'm going to go ahead and write that cross product, and I'm going to write the equation of the plane. And after we have survived the derivation, we're actually going to do an example. All right, so let me go ahead and erase real quick, and I'll be right back. So now what we're going to do is we're going to write the vector n as the cross product of these two vectors. The order really doesn't matter. I mean, you're going to end up with a negative of one or the other, but it's okay. We can write it as ijk. And I don't like memorizing the formula, so I do it as a determinant. And I get the partial derivative with respect to x of f evaluated at x0, comma y0, which I'm going to summarize as just as fx for space. And this is going to be 0, 1, fy. So when you do this product in the I coordinate or in the 1, you would eliminate this and you get 0. I got the negative. Okay. 0 times f of y minus f of x, which is okay. We can do the negative. I'm going to change it to positive just because it's customary to write it with positive. Now for j, you eliminate this row and this column, and you remember that you would multiply times negative 1, so you get 1 times f of y is f of y minus 0. But remember, for the j, you get negative f of y. And lastly, for k, you get 1. All right, so that is your cross product. I'm going to choose n to be the negative of it, just because it's easier. I don't know, I'm just used to writing it that way. So in any case, I get that that is going to be my my vector. So the equation of the plane, finally, we got to it. The equation of the plane, as by what I told you, is the partial with respect to x, evaluated x0, comma y0, times x minus x0, plus partial with respect to y, evaluated at x0, comma y0, times y minus y0. Plus, this is going to be a negative 1, so I should have put negative 1, of z minus z0, but since I have a negative 1, I put plus and I don't want to erase, I'm very lazy. z0 minus z, change it, equals 0. And then, customarily, people just add this z on both sides, and then they write this z0 as f of x0, comma y0, and then the rest just partial with respect to x, evaluated at x0, comma y0. How many times I want to say that? I don't know, many. Plus f y x y minus y0. Okay, I will erase. And that will give us the equation of the tangent plane. So it depends on the partial derivatives and on the value of the function. And if you think about it for 1 second as if we were doing two-dimensional, the equation of the tangent line was, well, you had, when you did it in parametric forms, if you remember, so you had the point plus the derivative of the x-coordinate times t, which would be kind of like the partial with respect to x, and then the change in x, and then the derivative of the y-coordinate, and then times the the t parameter. So it kind of resembles the same idea. You have a slope times an increment, slope times increment, plus a point that shifts your position to get you all the way back to the point of tangency. Anyways, it's similar. Nonetheless, we're now going to do an example and see how it goes. The derivation is the hard part. The example is easy. So let's go ahead and erase, and now we'll write an example here. I'm probably going to copy the formula here so we can use the whole board. All right, I'll erase and I'll be back in 1 second. All right, so let's take a look at the problem that is very similar to something we did in the, or I asked you to draw the graph in the previous exam. And it was just f of x squared, f of x comma y. We called it z because we were just doing the standard quadrics. So let's do something like plus 3y squared. And you guys remember that this had the shape, it was a paraboloid, and elliptic paraboloid because the cross sections are ellipses. So you had an elliptic paraboloid. That was a bit longer in the, I drew it wrong. That it should be longer in the no, it's longer in the x direction. I drew it right. Never mind. Even when I make mistakes, never mind. Just wait. I want to make another one just to make things well. Karma will get me. All right, so let's pick a point and let's find the tangent plane. So I don't know. Let's do 1, 1, 4, for example. So at the point, I'm just evaluating 1, 1 before. I don't know if this is any special point or anything. I just liked it. So I'm going to plot that point. So I'm going to say I'm going to 1 here, 1 in this direction, very not to scale, up to say there, which would be say 4. And I'm going to try to draw the plane that is tangent here. So it's going to be going kind of in this direction. So I'm trying to find the plane that is tangent there. So all I have to do, well, first I have to find my partials. So let's do fx of x comma y is the partial derivative with respect to x. So derivative of x squared is 2x. Derivative of 3y, y is considered a constant, therefore is 0. So just 2x. And for fy, x comma y, that's a funky y. X is a constant for the partial derivative. Dies when I take the derivative. How violent. Anyway, take the derivative here, I get a 6y. And then I just have to evaluate my partials. Let's continue here at the points given. So fx evaluated at, in this case, 1, 1. And that's going to be given by 2 times 1, so 2. And then fy of 1, 1, which is going to be 6 times 1, which is 6. So this coefficient is 2, this coefficient is 6. And now f of x naught y naught was 4. So z equals 4 plus 2 times x minus x naught is 1. 1 plus, can I fit it there? Probably 6 y minus 1 because y naught is 1 as well. Long derivation, extremely easy to apply as long as you remember your formula. But you know, if you forget your formula, you don't have to ask me for a formula. You just run through the derivation real quick and you're fine. I'm kidding. All right, so that's it for today for this video. Thank you for watching and I'll see you in the next one.